All right, this week's packet and our subject is all about exponential functions. So the word exponential should ring a bell. We've been talking a lot about exponents lately. First, about 2 weeks ago, we learned all of our exponent rules and we practiced with those for a week. And then last week, we talked about roots, like square roots and cubed roots, which tie together with exponents because roots can be written as fraction exponents and fraction exponents can be written as roots. So we've been talking about exponents a lot over the last 2 weeks. And this week is just an extension of what we've talked about. But this other word here is also important. We are talking about exponential functions. And the word function is something that you've probably heard in algebra, but maybe you haven't spent a lot of time actually thinking about what a function is. A function is something that has multiple variables in it. So, for example, you don't necessarily need this in your notes. I'm just putting this up here for your reference. You can put it on your notes, though, if you'd like to refer to it later. An example of a function would be y equals 2x minus 1. What makes this a function is that we can choose different values for x, and then we get different values for y. So the function part of it is you put in values for x, and you get values out for y. And one of the ways we learned how to examine a function is by making a table of values. So we could pick some values for x. Let's say like -1, 0, 1, 2. And we can plug them in for x, and then we'll get out a value for y. So if I put in -1 for x, then y would be 2 times -1 minus 1, which is -2 minus 1, or -3. So our y value would be -3. We could just do that straight down the list. If I wanted to put in 0 for x, then we'd have 2 times 0 minus 1, which is -1. So our y value would be -1. We could do it again. We could put in 1 for x. So 2 minus 1 is +1. We could put in 2 for x. We could put in anything we want for x, actually. And we would end up with points that we could then draw on a graph. So -1, -3, 0, -1, 1, 1, and 2, 3. So I'm just drawing these 4 points on a graph. Notice that they form the shape of a line. We probably should have known that because this is a linear equation, right? It's got a y and an x. We could find our m and our b, our y-intercept, our slope. So we did a lot of talking about linear functions, but we haven't really talked about functions in general. So functions don't all have to look like lines. There are different types of functions, and one of those different types of functions is exponential functions. So I just wanted to do this quick example at the top of the screen here to kind of orient us, to remind us of some of the things that you may already know about functions. And now we're going to talk about what's so special about exponential functions. So the definition of an exponential function is it's a function in which the y values have a common factor when the x values increase by regular intervals. So the y values increase or decrease by a factor, whereas the x values increase or decrease by regular intervals. The next thing that this definition says is that an exponential function does not have a constant rate of change. So the line that I drew up at the top of the screen, that has a constant rate of change. It changes consistently. It looks the same from here to here, from here to here, from here to here, from here to here. It doesn't like change partway through. You know, it doesn't go like this and then like this and then like this and then like this, right? It never changes. It's constant. It has a constant rate of change throughout. But exponential functions don't. They're very different. In an exponential function, y values change multiplicatively, and x values change additively. So those are some big words. Multiplicatively just means with multiplication. Oh man, I put my tablet on a magnet. It shuts it off. Give me a second. So multiplicatively means with multiplication. So your y values have to change by a multiplication pattern, whereas your x values have to change by an addition pattern. So what we're going to do is we're going to look at two examples where I show you what exponential behavior looks like. So this first example on the left is a table, just like the table of values I made at the top for this linear equation we were looking at. So we're going to pick some random x values, but we're going to pick x values that increase at regular intervals, okay? So notice the x values here that we've selected increase by +4, +4, +4. Basically what they're saying is pick x values that follow a pattern, an additive pattern. But now we have to figure out what pattern our y values follow. Is this an additive pattern or a multiplicative pattern, and how can you tell? So let's think through this. From 20 to 40, if we're using addition, then that would be +20, right? So is this the pattern we have? +20, don't write this down. Is this the pattern we have? +20, +20, +20? No, because that would go 20, 40, 60, 80, right? If we're just adding 20 each time. So this is not an additive pattern. This has to be something else. Is it multiplication? Well, to go from 20 to 40 would be times 2. To go from 40 to 80 would also be times 2. And to go from 80 to 160 would be times 2. That's looking good. I use a dot instead of an X, but you can put whatever you want there, times 2. So this is what we mean by exponential behavior. Your X's are increasing by an additive pattern. Your Y's are increasing by a multiplicative pattern. Notice how big our numbers are getting. It's not going 20, 40, 60, 80. We've doubled that. It's going 20, 40, 80, 160. So they're getting bigger faster. That's what multiplication does as opposed to addition. It will make it bigger faster. Exponential functions will have this type of pattern. So there's another example here I want to point out, and this example is to demonstrate a point. We say multiplication, but that could look like division as well, because multiplication and division are the same, right? Multiplication and division are the same because you keep change flip division, and that turns division into multiplication when you keep change flip, right? So they're the same thing, inverse operations. Now let's take a look at this example, and I'll show you what I mean. So first we need to look at how x is changing. When x goes from 0 to 2, 4, 6, 8, 10, it's counting up by 2s, right? We get a +2 in between each step here. So x, the change in x is additive. Let's look at the change in y. When we go from 64 to 32, well, we might be subtracting 32, but then look at the next step, from 32 to 16, and then from 16 to 8, and then from 8 to 4. What's the pattern we're noticing? Each step, we're dividing by 2. So dividing by 2 is how most people probably think of this, but dividing by 2 is the same as multiplying by 1/2. Multiplying by 1/2, multiplying by 1/2. So you could think about this either way. Dividing by 2 is the same as multiplying by 1/2. So if your pattern looks like division, it's also multiplication, okay? And by the way, if any of you wrote divided by 2 here, divided by 2, that is correct. I just want you to recognize that a multiplicative pattern could also be division, okay? Just like an additive pattern could be subtraction, because you can add negatives instead of adding positives, right? So don't let things like that throw you off. Okay, so let's talk about what these tables actually are. Oh, we're missing something here. These tables basically represent points on an exponential function. In the big box that has a blank that says exponential function, I want you to write this out. Y equals AB to the x plus c. This is the generic form of an exponential function. Now, when you're actually given an exponential function, A, B, and C will be numbers, okay? There won't be letters here. These will actually be numbers. So it might be like 2 times 3 to the x plus 7, okay? But there will be an x. That x will remain as an x. Remember, your function always needs to have an x in it because you have to be able to plug things into x. That's what a function is, right? You put things in for x, you get things out for y. So A, B, and C will be numbers, but x will still be a variable. And the other important thing I want to point out about this is the x is an exponent. You see how it's raised into the exponent position? Well, that's kind of weird, but we know a lot about exponents so far. One of the things we know about exponents is that exponents always have a base. What is the base of this exponent? B, just B. And that's really important. So I want you to make a note, either circle it or highlight it or underline it and write base. B is your base. And there are a lot of things about exponential functions that we can tell just by looking at the base, just by knowing what the base is. So let's talk about what some of those things are. Growth or decay. These are just words that we use to describe whether a function is going up or going down. An exponential function with a base larger than 1 is called a growth function. So if B is bigger than 1, so it could be like 1.5 or 10 or 1,000,000, okay? As long as it's bigger than 1, your exponential function is going to be a growth function. If your base is smaller than 1, it's called a decay function. So that could be something like 0.3 or 1/2. That would be smaller than 1. Okay, so it could be a fraction, it could be a decimal, but it has to be somewhere between 0 and 1. We don't have to worry about negatives. Your base will never be negative, so at least not at this level of algebra. So we don't have to worry about that. So we're just looking to see whether our base is a fraction that's smaller than 1 or if it's bigger than 1. Okay, so that's growth or decay. Next, we're going to look at the y-intercept. You guys already know what this is. Functions have y-intercepts. So just real quick, I'm going to scroll back up to the top of the page. The y-intercept is the point where your graph crosses the y-axis. So on this very first example we did, this function crosses the y-axis at -1. Exponential functions will have that kind of feature too. The definition of a y-intercept, you already know this, is the point where the function crosses the y-axis. But here's the important part. It's the point where x is 0. It's the y value you get when the x value is 0. That's how you find your y-intercept. And we will use this in almost every problem we do this week. The next definition you need to know is a word that maybe you have never even heard before. Has anybody ever heard the word asymptote? Well, I think I need an example to really discuss what an asymptote is very well. So you might want to jot this down in your margin. I'm just going to draw an example. Let's say I have this graph here. So I'm drawing a little graph, and I'm just going to put a shape on it. Maybe try to draw something similar to this. So notice this graph that I just drew. As the red part kind of gets further and further to the left, it looks like it's flattening out. Sometimes when we have a graph, it'll just kind of like go down forever. Like if it were going in this direction, it would go down forever. It would just keep going further and further down. But the graph I've drawn, if I continue this pattern out further to the left, it's like it's going to just keep getting flatter and flatter and flatter until it almost looks like a straight line just going left, right? If I were to visually continue that pattern. That is very common. That happens in functions all the time. So what we do is we say this line right here that our function is getting closer and closer and closer and closer to, but it'll never actually touch it. It'll never touch it and it'll never cross it. We call that an asymptote. And I tried to draw a dotted line. It's so small that you might not be able to see it, but there's like this dotted line that goes across here that my function is getting very, very close to, but it's never going to touch it. And we've seen plenty of dotted lines lately, right? When we did inequalities, remember, dotted lines are not solutions. Our function can never actually touch that. It can never be part of that line. That line represents a boundary that our function will never cross. So that's what an asymptote is. Asymptotes are always written in the form of a line. So the blue dotted line that I just drew on this screen, that would be the line, the horizontal line, y equals -2, because it goes through the point y is -2, and it's a horizontal line. So your answer, if the question is, what is the asymptote, will always have y equals and then some number, whatever number it goes through the y-axis on. So make sure you answer these in the proper way. For an asymptote question, if you were just to put the answer is -2, it would be wrong. The answer would be y equals -2 because it has to be the line, not just the number. Okay, now on to domain and range. These are concepts that I think you have addressed earlier in the year. Maybe it's been a while, so I wanted to reintroduce these. Domain is defined as the set of all x values that make the function defined. Here's the thing. We're not going to go into too much detail here. In a lot of other types of functions, domain can get pretty complicated. But with exponential functions, and only exponential functions, your domain is always, always, always all real numbers. That's it. So you will have every single problem in your packet this week. If you flip through and look at your packet, almost every single problem has a line for domain. They want you to say what the domain is. On every single one of those lines, you are going to write all real numbers. You don't even have to think about it. Let me explain what that means. The domain is the set of all x values we are allowed to plug into our function. In our functions, we're going to have like y equals, let's say, 3 to the x. So we're trying to figure out what x values we're allowed to plug into x. Anything we want. We can plug in positive numbers, negative numbers. We can plug in fractions or decimals. We can plug in anything to that x value. So our domain doesn't restrict what we're allowed to put in for x. There definitely are functions out there where there are certain numbers you're not allowed to plug in. For instance, if you're curious, I'm going to erase this example in just a minute. So look up on the board if you're curious. If I had the function y equals 1 over x, I'm not allowed to plug 0 into x here because you're never allowed to have 0 at the bottom of a fraction. because dividing by 0 is undefined. So 0 would not be part of my domain, but everything else would be, okay? So this is just a quick example of a time where you would need to actually think about domain. When we're dealing with an exponent, though, we're allowed to put anything we want in there. We can put a 0 in there. This isn't like a fraction. You can't have 0 at the bottom of a fraction, but you can have 0 in an exponent. So we don't have anything we have to worry about. Our domain is always all real numbers. Finally, we talk about range. Now, range is sort of the flip side. If domain is all the x's that can go in, range is all the y's that can come out. And the easiest way to find the range is to look at a picture of the graph. So let's go back to the example I drew on the margin of the page a minute ago. The range is all of the y values. So notice where my red graph is. My red graph will touch all of the y values everywhere from like here up. And notice this keeps going forever, so my range will keep going all the way up forever too. But none of these values down here, none of these y values will be part of my range because my function stops at that asymptote. Remember, I know you just learned this, but what an asymptote does is it represents a line that our function can never cross. So our function will never be below that blue dotted line, ever. It can never go down there. So none of these values can be part of our range. So our range here, if this blue line represents y is equal to -2, then our range would be y is greater than -2 because our function always has to be above it or greater than the line. So the asymptote and the range will always look very similar. One will be like y equals 5, and the other will be y is greater than 5. Okay, so they'll go hand in hand, and they'll always have the same number there. Okay, so that was a lot of definitions. I hope you've taken some notes here and made a few little maybe emphasizing marks so that some of the important information from these definitions stands out. But now let's take what we've talked about and apply it to a couple of examples. In the first example, we are given the function y equals 2 to the x. We're going to do a lot of things here. We're going to build a table, we're going to draw a graph, and then we're going to answer a bunch of questions at the bottom about this graph and about this equation. So let's start with building our table. We need to plug in some random x values, but let's be smart about this. Remember what we talked about earlier. We want our x values to increase at a regular rate. So notice in our examples earlier, we did like +4, +4, +4, +4, and then we did +2, +2, +2, +2. So we want to pick some kind of constant rate for these to change. And I'm also going to look at my graph. So my graph goes from -6 to +6. So I don't want to go too far outside of that, right? Because then it won't fit on my graph. So here are the values I'm going to pick. I'm going to pick -4, -2, 0, 2, 4. So notice those are going up by 2 each time. +2, +2, +2, +2. I did not have to pick these numbers. I could have picked -3, -1, 1, or I could pick, -1, 0, 1, 2, 3, right? So you can pick any values you want. Try to pick values that increase on a constant rate, and maybe try to pick some negatives and some positives and stuff so that you can get like a good spread on your graph. So once you've picked your x values, now we have to find our y values. So I'm going to start with the top one. So we know from the function that y is equal to 2 to the x power. So we're going to plug in -4 for x. So it'll be y equals 2 to the -4. Well, this is weird, right? A couple of options. One option, use a calculator, but that's not necessary because you know how to solve this. If you wanted to type in 2 to the negative 4 on a calculator, you would just type in 2. And then if you have a calculator on your desk, take a look at it. Or if there isn't one, grab one nearby. The exponent button, I know everybody knows how to type in like x squared because there's a little square button on the left. But if you want to type in a different exponent, you have to use the caret button that's on the right-hand side. So it's the button immediately above the division symbol. So you would type in 2 and then the caret button, and that'll raise your cursor up into the exponent position. And you can type whatever you want into that exponent. You could type in negative 4, you could type in 2, you could type in 0. So you can plug these into a calculator or you can calculate them by hand. I'm going to calculate them by hand. So 2 to the negative 4, does everybody remember what a negative exponent does to an equation or to a base? It moves it to the other side of the fraction. Remember that from 2 weeks ago? So that's going to push it down to the bottom. And when that happens, the 4 becomes positive. So we end up with 1 over 2 to the 4th. Well, 2 to the 4th is just 2 times 2 times 2 times 2, which is 16. So we get 1 over 16. So when our x value is negative 4, our y value is 1/16. Where will that be on our graph? That's a point, right? X comma y. Negative 4 comma 1/16 is like right here. It's really close to the line, but it's not quite there. I probably didn't even draw my dot close enough. It probably should be even a little bit closer, but I wanted us to be able to see the dot, so I had to make it pretty big. So that's where our first point would be. Let's plug in our next one. We want to find what y is when x is negative 2, so we plug in negative 2. So we get y equals 2 to the negative 2. And that becomes 1 over 2 squared. That's what a negative exponent does, which is 1 over 4. Or you could use your calculator on this. Plug it into your calculator. That is fine. Let's plot it. We have the point negative 2, comma 1/4. So that'll be about right here. It should be a little bit higher than our last point. So our next point should be maybe a little bit higher than our last point, but it's going to be kind of hard to tell because they're so close together. All right, let's move on to our next value. We've got x is 0. When we plug that in, we get y equals 2 to the 0. Anybody remember what a 0 exponent does? What does it do to that 2? What should this equal? Say that again, Joel. It does equal 1. Anything to the 0 power is equal to 1. So all of your exponent rules are going to come back to haunt you if you don't remember those. So this becomes just 1. So now we have the point 0, comma 1. That one's pretty easy to find on our graph. So that one's a little higher. Let's do the next point. We're going to plug in 2. So we get y equals 2 squared, which simplifies to 4. And that'll be this point right here, 2, comma 4. And last but not least, we're going to plug in 4. So we get y equals 2 to the 4th, which is 16. So that'll give us the point 4, comma 16. Which is all the way up here. Notice how fast our numbers are getting bigger, right? We go from 1 to 4 to 16. They really jump up there. So once you have your points plotted on your graph, we are going to connect those points with a line, but it's not going to be a straight line. You see, it's kind of curved. So do your best to draw this as accurately as you can. Yeah, close enough. All right, so let's talk about this graph. First things first, as it goes further and further to the left, this line is going to flatten out. So I'm going to draw it in red so you can see it. If I were to carry this out to the left, it would just keep going like straight forever, right? It's never going to take a turn and start going down. You know, it's never going to come over here and then just turn down for some reason. That will never happen. It will flatten out and it will go straight forever. That's the worst example of a flat line, but you get the point. So we can see that as this line is flattening out, it will get closer and closer and closer to that axis, but it's never actually going to touch it and it's never actually going to cross it. So pay attention to little things like that when you're drawing your graph. Okay, so let's answer some of the questions about this graph. Question 1, growth or decay? Is this a growth or a decay graph? And there are 2 ways to answer this question. The first way is look at your base. Our base is 2. If your base is bigger than 1, it's growth. If it's smaller than 1, it's decay. So our base is bigger than 1. This is going to be growth. That's one way to find the answer. The other way to find the answer is look at the picture. As we go from left to right, remember you always read from left to right. So as you're scanning from left to right, the graph is getting bigger. The graph is going up. So read it from left to right, watch it go up. That means growth. So 2 different ways to identify that this is a growth function. The next question is, what is the y-intercept? We have 3 ways to find this. Technically, it's only 2, but I'll point out 3 ways. So the first way we could find this is, hey, if you happen to have the y-intercept on your chart, use it. So here's our table. We found the y-intercept. Remember, the definition of the y-intercept is the point where x is 0. So if you have the x is 0 value on your table, then the y-intercept is right there. So our y-intercept is 1. So that's one way to find it. The second way to find it is just look at your graph. You can often just see where your graph is crossing the y-axis. That's at +1. So that's another way to tell what the y-intercept is. Finally, if your graph doesn't look super clear, or if you didn't have 0 on your table and you want to find the y-intercept, just plug 0 in for x. And then it'll give you your y. So a lot of different ways to find your y-intercept. Next question, asymptote. Remember, the definition of an asymptote is a dotted line that your function will never cross. It'll get closer and closer and closer to it, but it'll never cross it. And we have one of those right down here. So I'm not doing a very good job of getting these dotted line parts where I need them. But basically, the axis that goes straight across there is our dotted line. Our function will never cross that. We'll never touch it. We'll never cross it. So that is the line y equals 0. Domain is all of the x's we're allowed to put in to the function. And that's going to be all real numbers. This is not a trick. Your answer for the domain of every single problem should say all real numbers. Not a trick at all. The range is a bit trickier though. The range comes from the asymptote. So the range and the asymptote are tied together. If y equals 0 is the line our function can never cross over, then our range has to be everything above that. That's where our function is above that. So our range is y is greater than 0. That just comes from the asymptote. All right, so we have one more example. And our next example, we're going to go a little bit more quickly, but hopefully it'll come a bit more naturally to us. Start by picking some values for x. Now, we can pick any values we want. I kind of like what we did last time. That worked out pretty well to choose -4, -2, 0, 2, 4. So I'm going to do that again. But you don't have to. You can pick any 5 values you want to, really. Just try to pick something that's convenient that will fit on our graph. And for this one, look at our base. Our base is 0.5. We don't want to try to do these calculations in our head. So this is a good exercise for a calculator and for practicing using that exponent button that we were just talking about. So we're going to take our calculator. I'm even going to write down calculator. So we're going to write down type in y equals 0.5 to the -4. So type in 0.5, hit your little caret button on the right side, and then type in -4. One thing to watch out for, the minus button and the negative button are different. So if you type in -4, you will get an error, a syntax error. If you type in -4, you'll get the right answer. So we got 16 for this one when we type in 0.5 to the -4. When we type in 0.5 to the -2, we get 4. When we type in 0, we get 1. Remember, anything to the 0 power is always 1. When we type in 2, 0.5 squared, 0.5 to the 2, we get 1/4. And then for the last one, if we type in 0.5 to the 4th power, we get 1/16. You might be getting decimal numbers as your answers. You can leave them as decimals or you can convert them to fractions. Either way, we're just plotting these on a graph. So it's okay to leave them as decimal numbers or you can write them as fractions. Either way, we're not being super picky on this type of problem. So let's graph these. Starting with -4, 16. That's going to be way up here. -2, 4. 0, 1. 2, 1/4. And then 4, 1/16. So do your best to connect your dots with a curve. I'm a little nervous about mine. That's pretty close. Could be worse, I guess. So your curve should look something like this. Don't forget your arrows in both directions because this keeps going on and on forever in both directions. All right, so we're going to answer some questions about this function. First question, is this growth or decay? We have 2 ways to answer this. You can look at your base. If your base is less than 1, it's decay. Another way of answering this question is looking at the picture at the graph. You read from left to right. As you go from left to right, if your function is going down, it's decay. The next question is about the y-intercept. There are 3 ways to find the y-intercept. If it's already on your table, then awesome, find it, there's your y-intercept. Or if it's on your graph and it's a nice, neat intersection point, you can just find it that way, looking at the graph. Or you can let x be 0. Whoops. Anything to the 0 power is always just 1. So 3 different ways to find the y-intercept. Now let's talk asymptotes. We're looking for a dotted line that our function will never cross. and it looks like we're getting closer and closer and closer again to this axis, but never going to cross it. That's the axis, y equals 0. Our domain is always all real numbers. And our range is tied to our asymptote. We're just going to take our asymptote and change the equal sign to a greater than sign.